Hello everyone. Today I'm going to give our group cheering, and this paper is called AgentNet, the Decentralized Evolutionary Coordination for LLM-based multi-agent systems. Um, and nowadays it is very common that we use LLMs and to use LLM to form agents and to reason, right, to even handle every kind of multiple model tasks. But a single agent cannot solve everything, especially like complex and real-world problems. Most existing multi-agent systems rely on a central controller or predefined workflows, which creates a single point of failure, which means if the central controller goes down, the whole system cannot function because all task assignments depend on it, and limited scalability, which means adding more agents doesn't help much because the controller becomes a bottleneck and it cannot efficiently manage a growing team. And the rigid roles apparently means each agent has a fixed role, so they cannot flexibly adapt or take on new types of tasks. And on top of that, when multiple organizations want to collaborate, and the privacy concerns and the proprietary knowledge make it hard to share expertise. So we need a new approach, uh, maybe a decentralized, adaptive, and fault-tolerant multiple agent systems that can handle such dynamic tasks and involving agent abilities. Here, as the figure one illustrated, we can see the AgentNet handles nodes failure with superior grace compared to hierarchical systems. Like, if a path is blocked and the system doesn't wait for a master controller to reroute, instead, the agent routers autonomously discover a new trajectory. And this is a self-evolving topology adapts to the available expertise and the current system state. So here's how AgentNet tackles these problems. First, it's a fully decentralized. There's no central controller, and the agents makes their own routing and the task decisions and can specialize dynamically. And this makes the system fault-tolerant and self-organizing. And second, the network topology itself evolves over time. The agents and their connections adapt depending on the task demands and the performance. And that means information flows efficiently and the tasks are assigned optimally. And third, each agent learns partial successful task trajectories and pull the most relevant experiences when facing new tasks. They also prune old, less useful knowledge, so their expertise stays sharp. And importantly, to protect privacy, agents keep most data locally and only share minimal task metadata, which is great for cross-organization collaboration. Here, I'm going to start to introduce these mechanisms, network structure. First, we'll represent the network mathematically as G goes to AE, where A is the set of agents and E represents directed edges, showing task routing between agents. And it's initialized as a full connected graph. For each agent in this graph, it has a dual role, a router, and that decides where tasks go, and an executor that actually performs them. But unlike traditional multi-agent systems that rely on a central controller, here each agent here makes its own routing decisions based on local knowledge and memory and the task at hand. And this is what gives AgentNet a full decentralization. And the edges between agents are also dynamic. The Formula One show how it evolved, and it balances past interactions with the success of the latest task. And here the alpha is a decay factor, and here the S is a success metric. So a stronger collaborations gets reinforced while weak one fades. And for those edges with low weights, they will be pruned, threshold theta. And over time, this creates an evolving network, absolutely, where agents naturally form stronger pathways with collaborations that contributes to task success. And here we are going to talk about how AgentNet agents learn and specialize. In this multi-agent system, and each agent has two memory modules, as I introduced before. One for rotor decisions, which is represented as mRow, and one for executor actions. And these modules store step fragments, including the queries and the context so far and the action taken. And when a new task comes in, the agent retrieves the most relevant fragments from its memory. It uses the similarity of embeddings of queries and the contexts, which is a very common way, and which are the trajectory before the step to find the top key similar memories. And the decision making follows the React, which is also very famous architecture, including two steps. First is reasoning, and we input a task, context, and retrieve fragments, and then we generate the reasoning output. And the second step, in acting, we use that reasoning output together with the query, context, and the retrieved memories, and then generates the actual action, either routing, splitting, or executing. Agents here also has a fixed memory size, and it prunes the memories when it's full, and they use an LLM to remove memories that are rarely used or less relevant to tasks. So this part is about a dynamic task allocation in AgentNet. The key idea here is that there's no central controller, as I've mentioned many times, and instead tasks are assigned and rotate in a fully decentralized way. First, every task is represented with three things: the task description, the required capabilities, and the priority level. When a new task comes in, the initial agent is selected by matching task requirements with an agent capability vector. Here is CMI, which is updated over time based on its past performance, which I'm going to explain in the next slide. The system compares the task required capabilities with all agents' capability vectors and simply picks the best matching agent as the starting point. And once an agent receives its task, it has three options, which is forward, which means to pass the task to a better agent. And the second is to split, to break the task into smaller subtasks and handle what it's good at and send it to the rest of others. A third action is execute, of course, just to solve the task directly. And here, a very important design is when an agent splits a task, it only sends results without its internal reasoning. And this design avoids unnecessary information sharing and prevents errors from spreading across agents. And meanwhile, agents are continuously learning, and their capability vectors gets updated based on how well they perform on task. And this actually ensures the whole process forms directed as a cyclic graph, so tasks won't get stuck into loops. Now let's look at how agents improve over time and how the system keeps task routing stable. First, each agent continuously updates its capability after finishing a task. And the update rule is very simple. It's basically a weighted average between what the agent already knows and what is just learned. So if an agent performs well on a task, it gains new capability in that direction. And over time, this naturally leads to the specific specialization. And second, the key idea of task state is that the task context is only updated when real progress is made. For example, when an agent executes a step or completes a subtask, if the task is just being forwarded between agents, that is the first action, right? And nothing will be changed. And this design will actually ensures that the routing path forms a DAG, and in other words, tasks will not get stuck. To validate such framework, the AgentNet they use the three benchmarks across the math and the logic and the function calling domains, and they choose five different baselines of single agent and four different multi-agent systems as the baselines to make the comparison. And here we can see the results of the main experiment, and we can see the agent consistently outperforms all of those single agents and these centralized multi-agent systems, and we can see that they almost get all the best or the one of the second best results. And of course, they conducted a lot of more analysis based on this mechanism. And first, we are going to talk about the heterogeneous agents, how they affect the performance on the BBH task. And we can see they set four different scenarios. The first is fully homogeneous, which means all agents in the system are identical. The second is the LLM heterogeneity, which means the different language models they used as the backbone, but the capabilities will remain the same. And third is the skill heterogeneity, which means they use the same model but use different capabilities of those agents. And finally, it's the both heterogeneous, which means all the models and the capabilities are mixed and different. And we can see from the result that with three agents, the fully homogeneous team performs best. And this makes sense, actually. And because in small teams, uniform reasoning helps avoid mistakes and keeps coordination simple. But when we scale to 5 agents, the heterogeneous teams outperform the homogeneous ones, because here the diversity actually helps. It's very straightforward that the different skills and reasoning styles complement each other, and it's proving overall collaboration. And the evaluation study, the authors had conducted 2 aspects to analyze. The first is the rotor effectiveness. They tested this architecture against 4 variations: total random, the random operations, including the forward, split, and executing, and the random next agent selection, and the centralized global routing. And the result is quite clear that the design routing mechanisms are essential, because you see the performance goes up. And the second, they also test the evolution phase. The author compared it with and without evolution, and the difference is also very significant. That it goes from 77 to 85 in math, and 23 to 32 in the API bank, and 76 to 86% of the accuracy in BBH dataset. And here we have more analyses which are very interesting, I think. The first one is how they analyze how AgentNet handles scaling. The authors add more agents and increase the executor pool and compare the performance. And at a high level, the AgentNet scales smoothly when we increase the number of agents and the executor pool. And that's why the authors say performance improves slightly overall. But here's very interesting that if you look closely at the figure, There's actually a more interesting pattern shows that the performance doesn't just keep going up. It goes up first and reaches a peak at 340, this group, and then it starts to drop slightly. And I think it can be explained that the mechanism of finding next agent is quite simple and no special adjustment for such a large agent size. And on the contrast, I believe it's easier to collapse for so many centralized multi-agent systems, the traditional ones, when scaling up like this. Such so the results in such a diminishing returns pattern is, I think, is acceptable. And the author also conducted the experiments to observe the autonomous specialization. They fixed the executor pool at 40, but a varied number of agents. We can see with 3 agents, the ability are fairly evenly spread, and everyone shares tasks more or less equally. And with 5 agents, we start seeing clear specialization, and some agents focus on knowledge, and others on sequence, etc. And then scaling to 7 or 8 agents, specialization becomes even more pronounced, especially for complex tasks. And in other words, each agent dynamically refines its expertise based on the task it handles. And some agents become very good at certain skills. We can see that on the figure on the right side. And while others focus elsewhere, and all without any central controller. And this is a visualization of how this network evolve in different stages. And the authors, they ran a 5 agent system on the BBH benchmark, and this figure shows the network across the 3 stages from the initial one and the intermediate state and the final state. And at first, we can see that all agents are fully connected with equal connection strengths, and there's no specialization, and every agent can handle a task equally. And during the intermediate stage, we can see that the connection values start to differ, and some agents collaborate more closely than others. And finally, we can see the network clearly shows specialized agents with distinct roles and strong connections form between agents that work well together, improving overall task performance. And the system has pruned efficient edges and reinforced effective ones. And finally, of course, forms a highly specialized and efficient collaboration topology, which is in the right side of this figure. Now we can have a look at this case, this head-to-head comparison using GPT-4 Mini on the BBH dataset. And on the left, we can see we can have the React, the very traditional method, and you can see it struggles here. It tries to solve the problem in a single step without any collective reasoning, because it doesn't break things down, and it ends up with a wrong answer. You can see that. And when we use the AgentNet on the right, it takes a much smaller approach. It uses a multi-step workflow that automatically bypasses agents that doesn't have the right expertise. Instead, the specialist agents take over and break the task into smaller pieces and work through them step by step. So let's cover limitations and future directions here. First, we can see the heterogeneity is a challenge. And in real applications, the agents can vary much more widely in terms of models, tools, and data access. And this makes task coordination and resource allocation harder. And second, the router's decision-making is currently limited to a very small pool of agents. And scaling these to hundreds of thousands of agents is non-trivial, especially in heterogeneous setups where the strengths and the weakness differ. So a fortune direction, straightforwardly, is designing incentives for exploration And this will let AgentNet discover new agents or specialized capabilities, improving the adaptability and overall performance. And in conclusion, AgentNet shows how decentralized adaptive multi-agent systems can outperform the traditional centralized setups and improves fault tolerance and efficiency while supporting agent specialization. Overall, it's practical framework for flexible multi-agent systems in dynamic environments. And that'll be all for today's presentation. And if you have any question, please ask here, and I will stop recording.